I'll just do a quick recap of Brownian motion. So we're all on board again. So stochastic process, so that's collection of lots of random variables indexed by time. Time goes from 0 to big T. In the world of finance, we typically think of world as being finite time horizon, mostly because of policies we induce. But so T is going to be finite. So then you have your underlying probability space, always omega F, and then there's a filtration F of T and probability measure P. Brownian motion, you remember, it's normalized to be 0 to begin with. Increments are independent, right? BT4 minus BT3 is independent of BT2 minus BT1. And then the increments have a Gaussian distribution. And this is important that it's a continuous function on all omega. Okay, so let's carry on. The simple construction we did was, we said let's start with a simple and symmetric random walk. So xi takes value +1, -1 with probability half. Look at the sum. It's a nice random walk. It's also a Markov process. And we discussed what being a Markov process means. Let's just go through that one more time. So for it to be a Markov process, you want the following property to hold true, right? In the discrete time setting, Sn plus 1 takes any value small Sn plus 1, given the whole history, is equal to the probability of Sn plus 1 taking the value small Sn plus 1, just given the present, that Sn is equal to small Sn. And why is that true in our case? It's true because Sn plus 1, just one second, what happened here? Yeah, is nothing but Sn plus Xn plus 1, right? So given all of this, what we are really asking is, what's the chance that Xn plus 1 looks like small Sn plus 1 minus small Sn? That takes only two values with positive probability, +1 and -1. But in any case, it's independent of the whole history thus far. And it's exactly equal to the probability that big Sn plus 1 is equal to small Sn plus 1, given that big Sn is equal to small Sn. So you have the Markov property. Just to let you know what Markov property really means. In discrete settings, and we'll just kind of play with this definition and we'll get the intuition for it for the continuous setting. We probably won't define it, or maybe we will define it rigorously. But nonetheless, it's good to be aware of this underlying intuition. What are we trying to capture? Okay, then we said what we'll do is we will construct a process from this random walk. So we'll shrink the process, this path that you see of the random walk, we'll shrink it by a factor of n. So what happens at time, let's say 5, what happens at time, let's say n times 5, now happens at time 5. So you've shrunk it by factor of n, and you shrink the space by square root of n. So whatever happens at some level, now you divide by root n. This is for t being a multiple of n inverse. And in between, just take a linear interpolation at other points. Just connect linearly. So at least you have a continuous path. So for every n, you get a continuous path. And then it's hard work to show that in the limit also you'll have a continuous path, that such a thing will exist. But that's the work we will not do. Okay, so we constructed this, and then we argued that this process that we now have, this is a process for each n. This sequence of processes is converging to the Brownian motion object that we discussed. That turns out to be true, right? And this is known as weak convergence of stochastic processes. If you are interested in probability, it motivates why you should study weak convergence of stochastic processes. All right. But to see why this convergence should happen, well, property 1 is straightforward. Just by definition, that should be true. So nothing interesting here. Look at the increments. Btn4 minus bnt3, bntf4 minus bnt3. That's just this sum right here, right? Add the t's, which are multiples of 1 by n. And the tiny error comes in when they're not multiples of 1 by n, but that we can ignore. Similarly, bnt2 minus bnt1, this quantity right here. So you can see that they involve different xi's. So they should be independent, right? And you can also check that the variance of this guy is just equal to, what's the variance of this guy here? Anyone? It's not rhetorical, huh? Oh man, it's a question I'm asking you. How do you find variance of sum of random variables? Sum of variance, and then a constant just comes out as a constant square. So this will become T4 minus T3. Which is what we promised to you, right? We said this is what the variance should be. And then we said ki, uh, by central limit theorem, this guy actually will, when n becomes large, this will look like a Gaussian random variable. So that part works out. That it is converging to the right Gaussian distribution with correct mean and variance. Mean, of course, is 0 here. All right. So for all of these reasons, just kind of reiterating that, you look at this quantity right here, it's this quantity, and by central limit theorem, you divide by number of terms, that's root n of t, and you multiply by root t. So this guy converges to n01. You're multiplying by root t, so what you get is n0t. We're just recapping here, right? So you have faith that indeed the process that you constructed should converge to Brownian motion. And indeed that can be shown. So we have an intuitive feel for what Brownian motion is. We can also kind of approximately construct the sample paths with current computer now using this. And you'll see that there was nothing special about xi's being +1 or -1, right? All you needed was basically that the center limit theorem should hold. So for that variance being finite is enough. Okay, otherwise IID-ness. So all of this will go is true much more generally. Okay, so let's carry on. The point in this, what I've said here earlier also was made that although BT omega constructed in this manner can be shown to be continuous in T for each and every omega. And just be very clear what's going on, because if you're seeing this thing for the first time, there's lots going on. In your sample path, in your sample space, big omega, you have all these sample paths, small omega, right? On each small omega, you defined this continuous set of random variables, BT omega. Okay? Uh, so you look at this BT omega that you constructed for each T and collect the omegas where this BT omega process, which is now deterministic, is just a function of T now. Either it's continuous function or somewhere it's discontinuous. So collect all the omegas where it's continuous, put that aside. That set has to be measurable. Okay, it will be. And it has to have measure probability 1. So that's what we mean here. Right? Yeah? So that I'm not defined here. Even you can imagine it being kind of, R0t. So all functions from 0 to t, where the x of small t can take any value, any real value. So you can collect all those functions and you can define it on that space. That's a massive space. Now you run into all kinds of technical difficulties. But a better space, which you later kind of simplify to, is C0t, which is just collect all the continuous paths between 0 to t. Yeah. Oh, you don't want to go there right now. That's a massive exercise. What we'll do is, yeah, so you can, very good book to read is Shreyaev probability. He nicely spells all this out. No other book does that, so that's why I recommend it. Yeah. The set is yeah, non-probability of set one. All the omegas where it's continuous throughout, that omega has set as probability 1. What I'll do is in the November, I think week of November 12th, I'm not here, I'm traveling. So I'll request Sarvesh to give 2 lectures. One will be on variety of Brownian motions. This will be probably curiosity driven. I mean, as such, we don't have that much time to kind of have these deviations, but maybe we're kind of, but it would be interesting for everybody. Second lecture, we'll see what we want to have at that time. I don't know if we can connect it to finance, but maybe something in stochastic calculus will come up. So I'll ask you to cover that. Okay. Right. What else do I want to say here? Okay, now, so let's move on now. Uh, so Brownian motion is a martingale, right? So we've not really defined continuous time martingale, but we kind of know what it should be, right? Just replace the discrete indexes by continuous indexes, and you get a continuous time martingale. So in particular, if MT is a martingale, you want this property to be true. E of MT plus S given calligraphic FT, the filtration, this should be equal to M of T for all S and T, for all ST greater than or equal to 0. Right, this is a property for continuous time martingale, and technicality can be, okay, this should be true, right? For all T. So then you have a continuous time martingale. Okay. So I won't define this beyond this. This is exactly enough, actually. So now we want to show that the Brownian motion is actually a martingale. You know that Brownian motion is a Markov process, although we've not again spelled it out. But again, intuitively, you know, because the increments are independent, if I tell you the whole history at time small t, what happens at time s t plus s later only depends on the Brownian motion at time t. Because it really is a function of the increment. It's b of t plus independent increment. So clearly Brownian motion is a Markov process, but it's also a martingale. And the way to see that is that we look at this quantity, b of t plus s given calligraphic f of t. And this is all going to be always important, that you extract the independence out. So bt plus s minus b of t plus b of t, right? Bt is known, comes outside. The increment has mean 0. It's independent of the history, and it has mean 0. So this is the notation of independence. Okay, so we have this. So it's a martingale. And this, of course, is very easy to verify. Bt is a Gaussian variable. Absolute value of Gaussian variable is a well-behaved random variable with finite expectation. So everybody with me so far? Any questions? So that's the only new thing we've done so far. That, yeah. Yeah, so what's the question? Yeah. Yeah, filtration is defined on 0 comma big T. You have this increasing sequence of sigma algebras, which are all subset of F, and B of T is measurable with respect to F of T for all T. Okay. So these are details which should be spelled out. Yeah. Right. All right. Mm-hmm. Mm-hmm. This one right here, because the increment is independent of F of T. So then the conditional expectation is equal to expectation, right? E of x given y, when x and y are independent, is just E of x. And we know E of x is 0. Okay, so let's define stopping time now. Exactly again as before, except that now it's going to be exactly this. You know, tau is the stopping time if tau less than or equal to t. Yeah, I should have written these things down, but that's fine, I think, you know. And I guess just to be correct, so tau is a random variable on my space.
This is not an independent statement. I mean, this is a consequence of how you find out. So you don't really need the vector.
I mean, that's a definition of a stopping time.
I mean, you need it to be satisfied, but
Yeah, that's right. Yeah, yeah. But every stopping time has this following definition. So tau omega is a stopping time if it's a random variable. It's measurable with respect to sigma algebra, big sigma algebra F. And the set tau omega less than or equal to small t that set should belong to FT. So you go to and look at every omega. On every omega, you define tau of omega, right? And some of these omegas, tau omega is less than or equal to small t. Collect all those omegas now and ask yourself, does this belong to f of t or no? Okay, then we say, okay, for every t, this should be true. So then it's a stopping time. And what we are capturing is that this is an example of a random time which is not looking in the future. So this is implementable kind of, we can do action on based on this. We're not peeking in the future, basically. All right. So now we'll tackle the same problem that we discussed earlier. I'll just go through it quite quickly. You've seen this before. You look at, BT is equal to small a versus BT is equal to small b. So you have to pay more attention because earlier it was big A and big B, and now they're small a and small b. So focus. But minus small b. Okay. Okay. So we define the stop process, which again is a martingale. So I'm not proving to you that the stop process continues to be a martingale with continuous time. It's not obvious, right? We not proved this already. Uh,
We did.
no. Huh? See, what we proved is in discrete time, if I give you a martingale, if I give you a stopping time, then the stop process is also a martingale.
In continuous time, we don't know.
In continuous time, also the same is true. I'm saying this without proof. If I give you a martingale in continuous time, I give you a stop.
Would something like MCT and DCT do the job, discretize it, and
Sure, but it's a good thing to think about on your own. Try to make it happen on your own. Discretize it. See what are the issues that you come into. Because you're going to take a limit, right?
yeah,
And the results have to hold true in the limit. So, and yeah, so, because we've not even done Fatu's lemma. So it's a little extra work for you. But otherwise, Michael Steele is a good book. They've done this, so you can go through that. Okay. But we'll take it as a given right now. All right, so this is a martingale. It's bounded. So I can, exchange the limit and the expectation operator. So in particular, I can conclude that this was always equal to this, but this also implies that E of B of tau is equal to E of B of 0, hence that's equal to 0. You with me so far on this? Uh, see, the point is, yeah, this is important to get to this part. You agree that the stop process is a martingale. So in expectation, this is equal to, it's independent of t. It has the same value. That's true for every martingale, right? So the value is true even at t equal to 0, small t equal to 0. And since tau is greater than equal to 0, that's just E of B of 0. So this quantity follows. Now we want to argue that, oh man, sorry. Now we want to argue that, even E of B tau is, well, let me just do it properly. We know that B of t min tau is converging to B of tau as t goes to infinity. This is because tau is a finite random variable, right? Again, some argument is needed that tau cannot remain between A and B forever. If tau was infinite, then this would not work. Suppose my tau is a random variable which just says that you stay equal to, you never leave A and B. Well, what do I want to say here? I mean, I guess if I had a process which remained between A and B forever, then I'd have issues. Then this would not work. For that process, tau will be infinity.
suppose the stopping time. Sorry, it means
Meaning you never hit A and B, right? So I can give you a process BT, which is a martingale, but you never hit level A or B.
exactly.
So then this result will not go through.
But left-hand side, in any case, is converging whatever. It's B.
I mean, BT min tau will then be just BT, but it will not be converging to anything. Yeah.
We need the
Yeah, we need tau is finite. Yeah. That's a good question. Yeah. Bt by itself as t goes to infinity is not converging then. It's a process which is just expanding. Its variance is increasing with t. But it converges to b tau, yeah, uh, because tau is finite with probability 1, and because b t min tau is a bounded process, we can, since it's converging to b tau, expectation of this is also converging to expectation of b tau. But now, what's the expectation of b t min tau? Oh, I'm getting old.
So martingale is the expectation of B.
Yeah, we just discussed that. Yeah. So it's 0, right? Yeah, I didn't have up there. I showed it, argued earlier. But good morning, everybody. Okay, so is this clear that expected value of b t min tau is always equal to 0? It's a martingale is equal to e of b of 0. It's true for every t. So one sequence is always 0 and it's converging to e of b tau, right? So sequence of values which are always 0 is converging to something. It's only converging to 0, right? So e of b tau must be 0. क्या करें?
So that expectation to be, I think the modulus is fine. Expectation of the modulus.
Yeah.
On the right.
Uh,
Right, DC one.
yeah, I mean, see, bt min tau.
Your screen isn't showing.
Yeah, no, that we have to do. But this I'm saying is bounded.
We can't see.
Oh, okay. I said you're not seeing the computer.
Yeah, from the iPad.
Yeah.
Stop
All
sharing.
right, all right. Did we record the meeting?
Yeah, it's not recording.
Did you do it or did I do it?
Yeah, it's recording.
Oh yeah, it is recording. Good. No. Okay, good. Okay, can you see it now?
Yeah.
So my point simply was this is bounded in absolute value because it's less than maximum of A and B, right?
Yeah, then.
That's all you need.
That's.
Yeah.
Just, my point was that expectation is 0. Yeah.
No, I mean, because this is bounded, I know that E of B t min tau converges to E of B tau. I don't need absolute values for this statement. This statement is true even with the signs present. Just go back to how we proved dominant convergence theorem. Xn had to be less than or equal to y for all n, and then E of xn converges to E of x if xn converges to x. Okay? Without the absolute value. All right, I should erase all of this.
Just slide this video on the side.
What's that?
Slide this video on the side.
Oh yeah. All right. So good, guys. We're okay so far? Okay, now the nice thing about Brownian motion, as was true for simple symmetric random walk, because it was just taking values plus minus 1. For any other random walk, it would not have been true. That at the stopping time, you would not have been equal to A or minus B. But for Brownian motion, it's a continuous process. You will exactly be equal to A or minus B. Otherwise, you might overshoot. So that's why these calculations are exact here. Okay, so you go back and
If the BT is continuous and if A and B are real numbers, you might jump if you did not have condition. But because BT is continuous, so
yeah. I mean, if I give you a random walk which was not plus minus 1, then you could overshoot when you stop. Your stopping time is first time you exceed A,
yeah,
not when you hit A. Yeah. No, it's important because in those level crossing probability, you get bounds. You don't get exact. Now here we get equalities. ठीक है? So E of B of tau is 0. These probabilities sum to 1. Plug them in and you get that probability that B tau is equal to A is given by B upon A plus B. So very nice and simple, right? This is the kind of elegance you get for free in Brownian motion. Yeah.
Because in the discrete case, we do the first step.
Right.
What is the here?
Yeah, because you're not.
I mean, there's always a kind of first step is gives you an equation, and here first step will give you a ODE.
So you solve the
You solve the ODE. That could be one way.
here the power of martingale.
Yeah. But there should be a, so I don't have it immediately off my hand, but one, there's so much of nice structure to Brownian motion. You could discretize and do things and make everything work and not have to refer to martingales. Because it's true for random walks, just by one-step arguments, you can discretize, do one-step arguments, take the limit. That would also work. Yeah. Okay.
It's not.
It's not a simple, yeah, you have to do work.
You got n there, now n
Yeah.
goes with friendly.
Right. But with some results, they are true. So you just have to make it.
This general proof for any symmetric problem. Symmetric continuous.
This thing,
Be where symmetric around 0.
yeah.
Everything like that.
Yeah. It's a when you it should be a martingale, I guess. I mean, you have to be a little bit more careful about what you mean by if it's dependent, then things can go wrong. But all I mean is when you know something is true, then you should be able to prove it. Not that proof is self-evident. Then you just get down and make sure the proof works. All right, so this is also martingale bt square minus t. And again, we saw this for random walk, right?
This is just that. But
Yeah. So the same idea should work, but we'll do it here. We have to show this property, right? And how do we proceed? How do we proceed?
you can just say MD plus SSP. That BT plus S.
Yeah, I mean, it's always good to exploit the fact that the increments are independent.
Get rid of that way stuff, all of that disappears.
Yeah. That's right. So once you've written in this manner, now you just open the square up. You know how to evaluate each and every term. Right? So this term, because it's conditional expectation, same as unconditional expectation, and this is just equal to S, right? This comes out as it is. This is going to be 0, and minus t plus S is there. So you're left with bt square minus t, which is empty. Right? And again, boundedness and all is not a big deal. BT is a very well-behaved process. It has very light tails. No, not bounded. I mean, I meant the expectation, just showing that E of mt is less than infinity. You have to show this for all t, right?
But that you just get because normal plus square is also not too bad.
Yeah. That's what I'm saying exactly. Normal has super exponentially decaying tails. Even if you raise to some power, you have a random variable whose tails are going to be decaying quite fast. It won't take very large values with high probability. So you expect these things to work out quite easily. Is this clear to everybody what I just said? That Gaussian variable is kind of, I think it's a precise bound, 1 by root 2 pi x e to power minus x squared by 2. So it's decaying very fast. It doesn't take large values with high probability at all. So the moments and all, you expect them to be well behaved, and you can show them. Second moment, third moment, it's not going to blow up. What's that?
So equal.
No, it's inequality. It's not density function. It's a tail CDF.
Oh, this is that.
It's the integral that we are saying is bounded by this. Well, odd moments are 0 because of symmetry. Even moments are not 0. Yeah. I mean, the density decays exponentially fast, so moments don't grow very fast. Moments will grow, but they won't. Or they should grow, right? Yeah.
Each moment exists at the moment.
Yeah. Every moment exists. Yeah. Okay. So, the stop process will be a martingale because the Original process was a martingale, and it's going to be bounded again. So we can use the same argument to show that expectation of this guy is same as expectation of this guy at 0.
Just to be sure, by when we apply optional stopping,
Okay, so that's yeah, this
stopping time theorem, we saw that.
yeah,
stopping time
this is these notes were taken by ISI students, so that's her contribution. So she wants to be more pure about what we call it martingale stopping time theorem, but it's also called optional sum. I mean, martingale stopping time theorem has a few versions in continuous time. So she just said,
just
yeah, yeah. Martingale stopping time theorem. Right. I mean, you have to have a nuance between optional times and stopping times.
No, I didn't. I wasn't.
No, I'm telling you that's useful information because if this is in FT, then tau we call it to be an optional time. If this is an FT, then we call it to be a stopping time.
Stopping time.
So it's a nuance there, yeah, yeah. So, mm. All right, so we apply this here, but you see how nice this is. A square into b tau equal to A minus b the whole square, b tau equal to minus b. Do the calculations, you conclude that expected value of stopping time is A times b.
For the
Right.
BT guy.
For the
BT.
yeah, for the
They are the
for the
same.
time to hit either A or level minus b. Now this you might be able to do by symmetry, because you kind of know that can't see it. Where can you see it?
But in some sense, what matters
You go ahead.
I mean, how big your increments are mattering. Like normal is more centered towards 0, but if you have data distribution, it might be less than.
I mean, right, you don't want to go in by saying that let's not have normal and Brownian motion, right?
Oh, this is just for fun.
This is Brownian motion, yeah. So you don't want to talk about processes which are more noisy than Brownian motion. That's a little too advanced in this stage. Because it was very hard work to construct Brownian motion with no. Huh. Yeah, I mean, that's why I didn't even bring that in this subject. Let's not talk about that right now. Why would you call it optional? It's not so clear to me either. Yeah. Huh. Yeah, that's right. In discrete time, we had predictable processes. Yeah. The- Yeah, yeah. Let me just rephrase you. What you should do is, yeah, you find that way and see if you can make the argument work.
What is the argument?
So, Rakshit, you have a lot of thinking to do. But I mean, the point is to way to think about this is kind of, when you're going to A and B, uh, you exploit that property, you have a Markov process. So once you can set up kind of recursive equations, maybe when you go to, let's say, from 0, you go to either 1 or -1. For now, just take A and B to be integers and set up recursive equations. And from that, see if you can argue things and all that. But it's not as straightforward as you think. There's no kind of a clean geometric variable that pops out.
Each time you're failing or system.
Yeah, yeah.
Multiple steps between.
Multiple steps, but you can write a recursive equation then.
How can be a yeah, like,
What he's saying is, yeah, so that's what I think. That seems like you have a lot more thinking to do that one. But all I'm saying right now is, okay, tau goes up by 1, down by 1. That probability is not going to be unchanged. So there's a random walk embedded in your Brownian process. And you can exploit that. That's for A and B being integers. Then you can say this for rationals and then take a limit to something. Oh, come on. Okay, so let's talk about exponential martingale. This is a, it's far more interesting than it looks, this way of doing things. And we'll see some of it right now. But for the point is with Brownian motion, because it's Gaussian distribution at any time t, exponential moments are well defined. You don't have to worry about exponential moments suddenly becoming infinity. You know, right? The exponential moment is a moment-generating function. We know what the moment-generating function is. So let's see. Let's just do this. So the claim is I can find the exponential of theta times b of t. I can evaluate that moment, and then I normalize with it, and what I get is a martingale. So this process here is a martingale. And let's just check.
Theta q take theta.
Matlab, if it's going to be a martingale, on an average, it should not change, right? So e to power theta bt at t equal to 0 is 1,
Yes.
right? So now I want to normalize e to power theta bt in such a manner that the mean remains equal to 1, right? And that immediately suggests that what I should do is subtract minus theta square 2 by times t. Because we know that for Gaussian variable, with mean 0 variance t, this is going to be e to power theta square by 2 into t. We know this result, right? So this immediately suggests,
This is just the MTF.
this is the MGF, just the moment-generating function of Gaussian distribution. Everybody with me so far? Vedant, how's the world on the website? All right. Okay, so let's come here. So what do we need to show for it to be a martingale? We need to look at this quantity, right? M of t plus s, conditional on calligraphic f of t. So again, we'll get the independent increments to work for us, right? So we can write it in this manner.
So the calligraphic is
Yeah.
always information we have access to.
Right.
So when I write empty, is empty a part? Empty part.
I mean, right now, yeah, it should be specified, but all we really need is this. Uh,
That's empty part. That's nice.
it contains the sigma algebra f of t.
Right.
All the information captured by Brownian.
Question before,
Mhm.
asking whether empty is given to us as part of the.
Yeah, no, I understand. I understand. But if you know ft, then you know mt, right? Yeah. So it's now you're saying, so why should I consider smaller sigma algebra which makes mt measurable? You could do that. They'll be equivalent to
Yeah.
b of t. Yeah. But a typical way to think about this is that it's the underlying noise. It's a little tricky, by the way. People in finance made this mistake for the longest time. When we come to the right time, I'll mention to you, but they assume that the sigma algebra corresponds to underlying Brownian motion, but that's never seen in the real world. What you see is stock prices, which are functions of Brownian motion. So then the issue you mentioned actually becomes important. So your friend Krantikar made a huge stink about this.
So
Huh? I'll come back to it at the right time, but all I'm saying is when we model stock prices as function of Brownian motion, then to say that I've seen Brownian motion from time 0 to big T means that I've seen the stock price from time 0 to big T. But if I see stock price from time 0 to big T, that need not mean that I've seen the Brownian motion. Because there may be loss of information. So those are nuances one has to be aware of.
we are seeing the Brownian motion captures the entire information. Seeing that even applicable price.
Yeah,
Prices.
need not get you back. You need some assumptions about invertibility.
About
Yeah.
what?
Invertibility. Mm.
Yeah. But there-
Okay, all right. So now you've seen this decomposition now, right? I've just taken BT plus S, subtracted BT, added BT, brought the BT outside. Everything else is just a constant.
but wait, I understand one thing. How is the expectation equal to? Because that's just MGF of a normal.
It's MGF of a Gaussian variable that means zero variance S.
That is exactly that. No, but you're noting. Oh, okay, that is literally here.
That's exactly the MGF. Everybody knows the MGF of a Gaussian variable, right? Okay. Okay, so now you sort things out. And you get empty and then just empty basically, right? You can see this calculation. So it's a martingale. And it's non-negative, its expectation is finite. I don't have to worry about the absolute value and all that. All right. And E of m tau, this should be tau here, the stopping time. That's again going to be equal to E of m0, and that's equal to 1. Okay. Also, actually, I started doing level crossing probability here, but then I realized it's not that easy. It's easier in discrete time. So then I changed the title. So this should not be there. So let's just look at what's going on here.
Crossing was that thing you make bets with way to be.
Just give me 1 second. Yeah. I think this slide should not be there. That's all. Let's just come here. Okay, so let's discuss change of measure for now. We've not done that, but change of measures are incredible tool in probability and also in math finance. It's a huge tool to derive results, to transform quantities so that they become more tractable. The big idea is kind of easily seen in discrete setting. Okay. But before I do that, let me define P tilde of A as expected value of M of big T, indicator of A, where M of T is some random variable which is non-negative, whose expectation is equal to 1. So big picture is, I have a probability space, I have a random variable which is non-negative and which has expected value equal to 1. And the claim is now that random variable becomes a tool for reweighing probabilities.
It's T useful here, or can you just think of it as any X, like not indexed by time? Right?
T means it's kind of, it's measured by the big sigma algebra.
X. But there's nothing to do with time in some sense, other than the fact that this is just
That's right.
script element.
That's right. Yeah, I just need basically a random variable, which is non-negative and mean 1. Okay, so now the point is, with such a random variable, I can construct a new probability measure, P tilde. So everybody with me so far? Right? I have probability measure P on the space. I have a random variable M of T, let's say. Now I constructed a new probability measure P tilde. So that P tilde assigned to any set A is expected value of M of T, indicator of that set A. So why is this a probability measure? It's non-negative. Total probability measure is equal to 1. And it satisfies the property of countable additivity. To be completely nitpicking and technicalities to show countable additivity, you will need to use Monzon convergence theorem. It doesn't automatically follow. No, I mean, you kind of show that, okay, what do you want to show? You want to say that P tilde of union I equal to 1 to infinity is equal to summation P tilde I equal to 1 to infinity. When AIs are disjoint. So just take your, just take it for AN, for finitely many.
And one more, this gives you an impedance.
Yeah, yeah.
You're measuring, you're trying to measure A, right? MD is fixed.
Yeah, empty is fixed. For every A, we are assigning a probability to it. This guy just gave me trouble. So they should, I mean, if I was to do this completely rigorously, I'll talk a bit more about the underlying space and such things. I'm kind of going a little fast. but you can still see everything. So I'm just defined a new measure like this for every A in my sigma algebra. So for all A in F, I've defined this new measure. And it's a probability measure now. That's the main thing. So M of T is called because, P of A equal to 0 implies P tilde of A is equal to 0 by definition. Okay. So M of T is really the Radon-Nikodym derivative of d P tilde by dP.
So this D is notation does not really mean derivative. Right?
Hmm?
D was notation. It
Yeah.
does not mean derivative.
Yeah. Yeah, right now it's defined this way. dP tilde by dP is a random variable, which is notation this in this manner.
Did not mean derivative. It was
Yeah.
just give that inverse.
Yeah. Right.
How do you
But
take it by you don't have an underlying notion of what that D is doing yet? Then how do you understand that one?
well, it's a Radon-Nikodym theorem. If if P tilde is absolutely continuous with respect to P, meaning whenever P of A is 0, P tilde A is 0, then the theorem says that P tilde has a representation of the following form, where M of T is this random variable. M of T is F measurable. For this, everything I said was on the sigma algebra F. So Radon-Nikodym theorem guarantees you this M of T, and that's all you get. So and it's unique, as we kind of discussed last time. But really, the way to come to this is first do everything in a discrete setting. So let me just do in discrete setting, then I'll come to you, Gauri. So what's going on in discrete setting? I've just given you a random variable MT omega, which is non-negative, whose expected value is equal to 1. So MT omega, P omega, summed over all omega is equal to 1. That's what I've given to you, right? Okay. And I've defined by taking A to be just omegas in discrete setting, I can do that. I define my new P tilde to be just MT omega by P omega, meaning my MT omega in this case is just this ratio. So it exactly is the ratio, P tilde omega upon P of omega. So we are trying to say that, okay, this was fine. In the continuous setting, I could have put a ratio of probability density functions. That would also work. But more general settings, what do we have here? So that is defined through Radon-Nikodym theorem. So such a random variable exists, and we call it dP by dP tilde. And we call it a Radon-Nikodym derivative of between two probability measures. Okay. Any questions on this? So the point is, whenever I have such a random variable, I can construct a new measure. And whenever I have two measures which are, where one measure is absolutely continuous with respect to another measure, I have such a random variable. It's an obvious, trivial thing to say in discrete settings. It's true more generally. So Gauri, do you still have a question? Yeah, I mean, the way it's done is Radon-Nikodym derivative is between two probability measures, both defined on the same sigma algebra. So then such a random variable will exist. Now that random variable will not be measurable with respect to larger sigma algebra typically. So then that's a separate issue. So how the two are related, those are kind of very different issues. Huh? Uh, See, when you learn that probability measure extends uniquely, it extends uniquely from an algebra to a sigma algebra, not from a smaller sigma algebra to a bigger sigma algebra. Right? Yeah. Because smaller sigma algebra corresponds to few random variables, so it can't extend to bigger sigma algebra. So, with me so far? So we'll see that this guy is going to play a key role in Gerzonov's theorem. These M of T's basically. Because Gerzonov's theorem is all about changing probability measure from one measure to another on the Brownian motion underlying space. Okay, so we'll use that a lot in finance. But at the end, it's just this change of measure arguments, and at the end, this is just the likelihood ratio, the ratio of two probabilities. So that's the way to think about this. Let's do this all in the Gaussian setting. I have a typo here. So consider random variables b1, b2, all the way up to b of t, where b1 is normal 0, 1, x1. bm minus bm minus 1 is xm, and that's also normal 0, 1. And all these increments are independent. Okay, we just kind of extracted these random variables from a Brownian motion. Okay. So these are b1, bm have this Gaussian distribution that I mentioned to you with mean 0 under probability measure p.
Yeah.
Yeah. Yeah. Let x equal to x1 through xt. You can see I'm struggling with space here, and this should be a single bracket, not double bracket. So if you look at some random function, some function of b1 through bt, h of b1 through bt, and you ask yourself what's his expectation, that's just this quantity right here.
X1, X1 plus X2 dot dot, that's what you mean.
Yeah. Yeah, I'm struggling for space here. Okay. Into f of x1, f of x2, I'll integrate that. That's the expectation, right? Now I want to write this under another probability measure. So what's this probability measure? So let G be the PDF of n mu1 and P tilde be the probability measure under which the density F under P is now replaced by G. So it's a little bit loose statement, but all I'm saying is that under probability measure P tilde, all these variables x1, x2, xn are not n01, but they're n mu1, but they're still independent. Okay, I just constructed a new probability measure here with this property. Okay, now I can re-express this expectation here as follows. I just divide by gx1 through gxt and multiply by gx1 through gxt, right?
Should have a good close form because it's
That's right. That's true. I mean, all I've done is I've looked at this expression, I've divided this by gx1 through gxt, and then I multiplied by the same quantity, right? So nothing fancy, basically. G is just the probability density function when the mean is mu and the variance is 1 for a Gaussian random variable. So everybody with me so far? But the point is, and this kind of brings home what we are doing, right? Oh man. So it's not entirely my fault. This guy just refuses to stay. All right. So now it's an expectation under with these densities, right? So it's an expectation under P tilde of a random variable which is MT times H B1 through BT.
empty, we're calling this guy.
The likelihood ratio.
Yeah,
Yeah. It's exactly the quantity you need when you go from P to P tilde. MT would be ratio of these probabilities. So it comes to, as Rushil had said, it simplifies to this quantity. N mu1.
PDF of N. F is PDF of N01. G is PDF of N mu1. And because
Right.
they're independently opened up, then exponentials that add up.
So, I mean, the numerator is product of e to the power minus xi square by 2, and denominator is product of e to the power minus xi minus mu the whole square by 2. That's different. This is change of measure. I've not said key let yi be some xi square or some function of xi. I've not done that. So that's another technique altogether, change of variable vis-a-vis change of measure. It's interesting because, these change of measure techniques are very useful in Monte Carlo simulation. You want to evaluate some quantity EP of X. Under simulation, what you can do is under probability measure P, you can generate many samples of X and take their average. And that tells you what EP of X looks like. But what you can also do is you can express this as EP tilde of MX as we've done, and then generate samples under P tilde of M times X. IID samples and take their average, and that also converges to the same thing. Right? So this is Monte Carlo use of importance sampling.
And the point is that sometimes people will get you better confidence about.
That's right. It'll be better. But where I'm going with this is that this is common, but you can also do change of variables and re-express EPX as some other expectation, and that gives you another way to do Monte Carlo. It's not probably well conceptualized, this idea. I've always kind of applied it here and there, and seen other people also apply it now, but I think it needs better treatment. All right. So yeah, I mean, this was the point that in this case you have this quantity right here. And this quantity we know, this. So I guess one more thing you can see from here, which I'll tell you later, that this M of t that we've constructed here is actually only a martingale.
Every time.
Yeah.
But what's the time steps?
In this case, it's just these t variables.
Oh, okay. So in this specific case, not in,
Not in the specific case, but this will extend. But
but in the case when you think of a sequence of variables, then each of them are ideal.
Yeah.
Then
then
this is
this is true.
right? Otherwise, you don't connect on the expectation.
What's that?
Say it's not a ground says no ground and water. And G is also not a new one. Then would it still be?
Yeah.
It will be.
It will be. Yeah.
You just need independence.
Yeah. You just need independence. Yeah. Right now it's hard for me to say if it's true more generally, but independence will certainly suffice. Yes.
The expectation of a function of inputs and your sequence in range of some next one range of inputs.
Yeah. Right.
For each of them, you do a change of measure.
Mm.
Using this data. We're saying that those changes of those
Yeah. But let me just kind of relate this to what we've been discussing. 'Cause something has gone wrong here. All right. Not quite sure what's going on. Okay, the point was this. This quantity you've already seen, right? Right? And this was martingale that we saw. And we saw it had mean 1. So in particular, this can be used for change of measure. Right? And that's we've kind of shown that the other way around, that this quantity comes up naturally as a change of measure when we look at the density of normal 0, 1 as measure corresponding to density of normal 0, 1 for all the random variables, and measure corresponding to normal mu 1 for all the random variables. See, because if you go back to this quantity right here, this h is a general function. I can take h to be the integer, to be an indicator of any set A, and then I recover my old relationship, right? EP of I of A is equal to EP tilde M of T I of A. Right? So this M of T was exactly what we started off by. It's a random variable which has mean 1, non-negative. It gives us new measure. So yeah, I mean, I guess where I'm going with this is, I've just introduced you to this idea of M of T to get a change of measure. M of T is a radon-Nicodemus derivative. And more simply, think of M of T as just the ratio of densities or ratio of probability mass functions. That goes a long way.
That is not normally distributed.
It will still be a martingale. It will still be a martingale, yeah. Let's take that as a quick classroom exercise. Do I have space here? So E of product of, let's say, I equal to 1 to t plus 1 fxi gxi under f of t, right? How do we proceed? And this is going to be a martingale under the measure p tilde. Now you can see that the product terms come outside, right? They're known already. So this is equal to I equal to 1 to t fxi by gxi, and then I have expectation of the remaining guy. And the remaining guy, because of independence, is just expectation of fxi gxi. And that, if you open up, I'll just do it very quickly here. Integral of fx by gx over all x into gx dx. Right, I'm finding the expectation with respect to density gx, right? Xt plus 1 has density gx. This and this cancels. This is equal to 1. Right? Yeah, so all you needed was independence. Clear? I'm looking for a green light.
Yeah, I mean,
Okay.
of course. I mean, I'm going to sit down again on this later, but
I mean, what have we done? Just, huh? Well, we're integrating with respect to g, right? So we're just canceling. The new measure is with respect to g. Right?
So it's being done. It's being done.
Yeah, right now it's being done.
It's actually,
So we'll show this in a continuous time. We'll see that the Gaznov's theorem, the likelihood ratio will actually be a martingale process.
then how do you make sense of the product? It's being
Well, so product is exponential of the sum. This is a great point, right?
Yeah.
And then what do you think? How do we go to continuous? Exponential of a sum in discrete setting becomes exponential of a integral in continuous setting. Yeah. Yeah. So all of these are very naturally motivated. These are questions that come to everybody. Well, this has to extend now. How do we do this? We need a clean theory. So we need to understand what that integral is going to be. That gives rise to Ito's integral. All right. How are we doing on time?
one.
One more?
ठीक है.
ठीक है. So this is just kind of taking away the mystery of M of t. M of t is nothing but the ratio of the densities. That's the big picture point being made here. ठीक है? All right. Okay, now let's do something very interesting with Brownian motion. It's called the reflection principle. Again, I'll kind of not do this thing entirely rigorously, but still you'll get a flavor of what's going on. I didn't realize Manan was in the class. So far away. Okay, so we are going to look at B star T, which is the supremum maximum of the Brownian motion process till time small t. Okay. So Brownian motion is a path going on like this, but maximum process is an envelope on this path, right? So once the Brownian motion goes down, that just remains constant. Right? So let tau be a stopping time, but it's a very important process because with stock prices, with securities, you worry when does the process ever cross a threshold? Meaning, is the maximum beyond the threshold? So it comes up very naturally in these things. So let tau be a stopping time. The process bt plus tau minus b tau. So we look at what happens to the Brownian motion after the stopping time. And the strong Markov property is that continues to be a Brownian motion independent of f tau. Let me put it differently. Bt plus s minus bt. Let's call this m of s. You can see that m of s is actually a Brownian motion by itself. M of 0 is 0. M of s continuous paths. The increments of m of s are independent. They have this Gaussian distribution, they're continuous. So m of s is a Brownian motion for sure. Okay? The question now is this also true? After a stopping time, if I see the process evolving, is that still a Brownian motion? That's an interesting question, right? And because it's a stopping time, you expect this to be true. Hmm? Why is? One is a stopping time tau, it's a random time. Other was a fixed time. So that was weak Markov property. Now this is a strong Markov property.
Wait, to me, weak Markov property is just that you're only dependent on past.
Tau is just a fixed time.
Yeah.
And the strong Markov property is tau is a random time, random stopping time. So this does require a proof, huh? It's a fairly it's a fairly demanding proof. We would of course do that, but we'll assume this strong Markov property, and we'll see consequences of this.
T is more, just be sorry. We don't care if T is less than equal to T, tau is greater than equal to tau or anything.
मतलब T कहाँ पे आ रहा है?
T plus tau.
It's, you mean here, in this guy here?
Yeah.
Yeah, T is non-negative, right? T is non-negative here.
Sure. But is it after tau or before tau? That's the question.
No, but T plus tau is after tau if T non-negative. That's all you need, right? That's all you need, yeah.
Oh, this is you just you can
Yeah.
shift it back.
Just, I give you a path
I'll chop the first tau.
at the stopping time, just take the path thereafter. Huh.
That's simple.
You know? Yeah.
And then you expect
This to be, yeah, it's one of those things that, okay, if somebody proves it for you, it's not a big deal. It had to be true, yeah. I mean, it'd be a really surprising thing if it was not true. Then you'll want to wonder what happened. All right. So we'll use this property now. We want to get handle on this random variable here, the maximum of the Brownian motion. So probability that the maximum exceeds x and at time t, b of t is less than x minus y. Okay. Level x, this is time t. So we are saying, okay, this is your Brownian motion. It went here, and let's call this y here. This distance becomes y. And the chance that it kind of crossed this, but then it came down like this. We are collecting all such paths and saying what's the probability assigned to those paths, right? The reflection principle says that what happens after you hit this point x, because it's a stopping time, is independent. And because it's Brownian motion, it's symmetric on both sides. So this path will have a corresponding path, which is a reflection. This is the beautiful part here. I think it looks like this. Right? So this path has same probability as the reflected path. For every such path, you can say that. Now let's see what that means. So BT star, B star T greater than equal to X, and BT minus B tau X is less than equal to minus Y, is same as BT star is greater than equal to X, and BT minus B tau X is greater than equal to Y, right? By symmetry. And this, and this is just BT star is greater than equal to X, and BT is greater than equal to X plus Y.
what is I first time.
This one right here.
Yeah, how do we say that BT minus B tau? What is B tau?
Tau X is stopping time when you hit X. It's the process at the time when you hit X. So if BT star is greater than or equal to X, that means you must have hit X by that time.
Okay, so B tau x is equal to x.
Yeah, B tau X is equal to X. Yeah. And it exists because you're looking at paths where it exists. Uh, Huh? BT star is the star of the show. It's this guy right here.
How does B tau s become X?
Huh?
B tau s becomes
It's the Brownian motion at time tau X. Tau X is the time when it hits X. Have I not defined it? Oh, small mistake. First time we hit X. Okay. So this should be defined. Okay. So now I'm reflecting this right here. This is the interesting part. Ki this quantity right here, less than or equal to minus y, because it's independent of whatever has happened so far. So this requires some intuitive kind of leaps. This is not being rigorously shown. So bt minus b tau x less than or equal to minus y is same as bt minus b tau x greater than or equal to y, right? In particular, these two joint probabilities are equal. So b tau star greater than or equal to x, b star t greater than or equal to x only depends up till time tau star x. And then the other event is after tau star x. So the two are actually independent. So that's why I can do this. Symmetry argument is key. Bt minus b tau x is just Brownian motion, right? After tau x. So whatever be tau x, the chance of it being below minus y is by symmetry equal to chance of it being above my y. Because Brownian motion is symmetric, right? See, this is true independent of the time. Whatever the stopping time is. Given the stopping time, chance that you go up in 2 seconds or you come down in 2 seconds by the same level has the same probability. And 2 seconds can be 5 seconds also, 20 seconds also. So there are, some subtleties involved here, but these are all acceptable subtleties. We know that they should be true. Okay, so
That even if I look at x, what is the probability that x will go higher? It's the same as going higher. That's what you're saying.
yeah, from this point onwards, in this picture, oh, there must be yeah. From this picture, for every path that goes down, is a path of equal probability that goes up, right?
Follow the Brownian being found.
Yeah, yeah. But more than that, right? Yeah, yeah. Independent, symmetric, all this.
Marco replies.
Markov follows from independence, yeah. Markov imply independence of increments. It doesn't imply that they have the same distribution. That's right. Okay. So now we are here, right? This just means that BT is bigger than x plus y. And if BT is bigger than x plus y, then clearly B star T is bigger than or equal to x. So this is exactly the probability that BT is equal than or equal to x plus y. Right? So we got this very nice expression.
What you're saying is that if you look at B hat, what is the probability that it moves higher? Okay.
So what's B hat T?
B hat is looking to find about that.
B star T.
B star T.
Yeah.
That is B.
Oh yeah, B hat T is there. Yeah, that's right.
T plus tau x.
Okay, yeah, yeah. Yeah, so
So what you're saying is this is just equal to the probability of your.
we are saying much more than that, but yeah, it's an important piece. Yeah.
It's equal to also probability of B hat T greater than equal to y.
That's right, yeah, yeah. I mean, what's nice is that this is true independent of time, right? Whatever be the tau x can be 5, 15, 20, it's always true. So it's a subtle result.
Yeah, but we had tau, we had t depends on tau.
Yeah. But the fact that it goes up or down doesn't depend upon tau. The equality between them doesn't depend upon tau.
And this needed a strong marker for
Yeah.
the first step.
Yeah. 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 Right after the stopping time tau, the evolution is just a Brownian motion starting all over again.
But also, is it the same Brownian? As in, is B hat, oh, Brown motion is always.
I mean, I've given you a collection of random variables. You go to time tau, collect the path thereafter, put them together. That's a Brownian motion. Yeah. Hmm. Yeah, it's a well-defined object. It's not like, yeah. Right. Okay, so what did we achieve? So this is an artistic rendition. So I say, a principle say, after hitting X, the path A and the reflected path are equally likely. In your mind, replace the lines with the reflected, non-differentiable Brownian paths. Okay. All right. So what did we get by doing this? So what we got is this, which is okay. You know, how do we use this? How do we use this basically, right? And the way we'll use this is we'll take Y to be 0. Okay, and then we'll extract some result from it. So let's do that here. So what do we have? We have probably that B star T getting equal to X. Now we've shown is probability B star T getting equal to X and BT is less than X. Right? No, have we not shown that? I mean, I've just decomposed this as two events, this plus this. Right? And what we've shown is that this quantity here is probability of BT greater than equal to X. That's what we've shown. Because once you've crossed X, whether you go or whether you go up or whether you go down has equal chance. So the fact that you were down is same as the fact that you were up.
Missing like inequality.
I mean, even if we were, these are zero probability events. Yeah.
And you ignored that. No, no, it's great. In the earliest one you had, that inequality, that's
Yeah. So you're saying here we had inequality. Yeah, that's right.
that's
It's a zero probability, just add and subtract. Yeah. Okay. So now what have we shown? We've shown that this is equal to this quantity right here. So and this of course is also equal to this quantity right here. So what we get is that this probability right here is this probability plus this probability. So it's 2 times probability that BT is getting equal to small x. So is this clear? We have a precise definition of this envelope process, the maximum process. We know exactly what the tail CDF is, hence we know what the CDF is, hence we know what the PDF is. So we know everything about this. So quite elegant and beautiful, right? You won't get this in other processes so cheaply. So Brownian motion kind of becomes, your go-to object.
in that sense, any Markov process
Right.
is also martingale,
Hmm.
which is symmetric.
Mhm.
Just these three things.
Without jumps and all that, continuity is very important.
Or two rechecks.
At b tau x, we were exactly equal to x. Yeah.
Again, the point is there are not too many processes which are all continuous. Oh, if you all of that, then you probably.
Yeah, then you're Brownian motion. Yeah, that's if and only if result.
No, just the difference is normal distributor. Yeah, sir, that's it. Increments can be distributed from other distributors.
Yeah. Yeah, yeah. Increments can be from other distributions.
But this is,
Yeah, but you won't get continuity then.
oh, continuity is only a not. And that's what I'm trying to say. Very few class distributions. It may not be. Take
What's
it
that?
as take it on this. Negative one. Yeah, I'm not.
Yeah. No, so I forget now. The point is, suppose I give you independent increments, stationary increments, meaning the distribution only depends on the length of the interval. And it doesn't depend on where the interval occurs. And I give you continuous paths. Do I get a Brownian motion? That's enough, right? Yeah, yeah, that's true. So I actually don't need to argue that uh, I don't need to argue that the increment has a Gaussian distribution. It has to have a Gaussian distribution. If I just give you independent increments in a process which has continuous paths and the increments are stationary, then it has to, then stationary meaning the distribution depends on the length.
I see. Oh, then it
Of-
has to run.
Be a problem.
Then it has to be a Brownian motion. Yeah. So that's the result. That's what.
Exactly. Not even the small graphs, just run.
Just Brownian motion. Yeah. 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 So we'll see this Levy-Kinchin result later. Maybe we can at that time see this again. Okay. So we've got this now, right? Are we doing on time? Okay. Chalo, so let me just define this quantity. This is an interesting quantity also. Huh? It's when did you hit level A, right? Tau A is the time at which you hit level A. It's random, right? On different paths, it takes different values. So it's a random quantity. And now you can say, okay, let's find the distribution of this time to hit level A. But the important observation is as follows. The event tau A is less than or equal to T. The fact that you hit A before time T is same as the event that the maximum process at time T is more than A. If you hit A before time T, right, then your maximum must be at least A. So these two are identical events. They are the same probability. Okay. So now we know this probability here. Okay. So we can evaluate this probability right here. Okay. So far, no mistakes. I have my fingers crossed. See, BT greater than or equal to A. It's correct. So BT is just normal 0 T, right? So T comes in wherever the variance should come in. It's just the variance. No?
Square. Now it got
No. It's exactly correct.
two sigma square. No,
Yeah, so it's
e to the power negative by 2 sigma
see
square.
it's 1 by root 2 pi sigma into e to the power minus x minus mu by
Variance is t, not t square.
yeah.
Sigma square, yeah.
This confusion continues to happen. Yes. You'll have to teach year after year to not have.
But what is the cell?
Well, so we got an idea now of what this looks like. We have an expression for the CDF of tau A, time to hit A. We have an expression for it, right? Suppose I want to find now the expected value of tau A.
Then you can easily check.
Huh.
Now you just integrate that.
Now I can just integrate, right? What do you think the answer is going to be?
For what?
For a Brownian motion, expected time to hit level A.
Okay. Sorry, more.
How much time will it take to hit level A?
E to the power negative a square by
But Chalo, that's redeeming. One by that helps. What do you think this time is going to be? Brownian motion is there. Say A is 1. How much time will it take to hit level 1?
Oh yeah, no, you told us this is infinite. No, it takes entire time.
This is infinite, yeah. Because it's like a simple random walk we've seen, right? It takes to go to +1, it takes. Because the problem is this, let's say simple random walk. On many paths, it will happen fairly quickly. But then there's some paths where you go to say -5 or then you're not going to come back. Then you come back for a very long time. Because the further you go, the chance of going further down increases and all that. So in expectation, it becomes infinite. But this is a well-defined PDF in the sense that if I let t go to infinity, this probability will go to 1.
But just to be sure, let's say it takes infinite time to reach, not to be greater than equal.
I mean, it's
Continuous at the same.
yeah. But you should check that this probability here Come on. This probability should go to 1, right? For this random variable tau a to be finite, probability of tau a being less than infinity should be equal to 1.
T goes to infinity.
Right? For it to be finite. So that you have to check that as we let t go to infinity, this quantity is exactly equal to 1. How will you show this? Not so easy, right? From here. Of course, that of course will work, yeah. Right.
It's just a simple application of DCT.
DCT, right?
Is it DCT? No, because you know what's going on in the yeah, DCT will do it. DCT will do it, yeah, sure. Well, e to the power minus z squared by 2t is still bounded by 1. Yeah. Okay. Sure. ठीक है. No, but you know, there's this issue of A, right?
So what I'm thinking is that at least you can hit
See, this is not minus infinity. That will A is the
As t goes to infinity, in p of tau a less than equal to t. P of a by square root t. So a by square root t goes to 0. P of a by square root t.
So you need a change of variables, right? No, you need a change of variables, right? You can't just do it.
because no matter what I can bound this further by the integral from minus infinity.
No, you can bound this, that's okay. But at the end, but we have to evaluate this integral, right? Oh, that bound goes to 0. Okay, then that's fine. Yeah. Yeah.
what are you taking for T?
But in any case, I think if you were to just do a change of variables, make the variance equal to 1, the proof will be much simpler. That will make it much clearer.
Okay.
Okay, so let's see now. Okay, it's time now, so we'll come back to this. But the bigger point when we come back to this is that it's going to look like this quantity right here. There's a t raised to the power 3 by 2 here, and something which actually becomes closer and closer to 1 as t goes to infinity. Right? E to the power minus a square by 2t becomes closer and closer to 1 as t goes to infinity. So this quantity is not going to play a role. While this remaining part, and I'm saying play a role in the sense when if you were to integrate this, you know, to find the mean and all, 0 to infinity, t into fat dt, this is not going to play a role in determining whether mean is finite or not. But t times t to the power 3 by 2 in the denominator gives you 1 upon t to the power 1 by 2, which does not integrate. Yeah,
Oh, this is why it's infinite.
that's why it's infinite.
Also, the Levi distribution, the Levi distribution is nothing but this stock. So it has a parameter A. And we think of it as the probability of
No need to, I mean, see, A is just any level, it's fixed.
yeah.
Time to hit any level A on average is infinite. So A is not really playing a role.
There's no parameter. It's
Yeah,
at X is just probability from round to quotient reaching X.
yeah. For reaching any time is going to be infinite. Yeah, hitting any level is going to be infinite on average. We'll do this next time, huh? Okay, we'll start and go through this.
The Levi distribution.
Why, this, where did I mention the word Levy? Huh?
Yeah, I'm reading that.
Oh, okay. Okay.
I'm reading that.
No, I'm confused because we used the Levy-Kinchin theorem, huh? Okay. Reading from here. So Levy distribution, that's right, yeah.
It needs A and B. That's what I'm thinking. A is just a parameter of the
Yeah, it's time to hit A, right? So it's still a finite random variable.
Levi distribution is just the probability of grounding motion.
Ever hitting level A. Time to hit level A. Time to hit level A.
So F of A is just that
Yeah.
probability.
So it should depend upon A, right? As A becomes larger, the time should become larger. Yeah. Right. Okay, so we'll come back to this, I guess, next time. Bye, everybody. Any questions on the web?
Small questions. Previously, we did not have a